Uh, so last time we solved, I think we talked about F, P, and I can't remember which other one. I think A, right?
Yeah.
And some of you did try them. So let's take let me just quickly go through what I have here. Right, so this F was the first one we looked at last time. This was the one where we want to find a answer key that maximizes the lowest possible score, okay? And the way we did this was, in fact, a simple naive solution works, and the naive solution says, sorry, the naive solution did not work, where the naive solution was to try and pick the majority in each column. And we talked about why this wouldn't work. You can look at the slides later. And then the correct solution really involves checking all possible correct answers. And if you just generate all the possible correct answers, which, by the way, because these are true-false questions, there are, for n questions, you get 2 to the n different possible answers. And for each one of them, you figure out the highest score for the worst performance. And because there are k questions and n individuals, the amount of time it takes is proportional to n times 2 to the k. And if you do the math, this is roughly of the order of 1 million. Okay, and we figured out that this works. I think people tried this, right? And got it to work. Is that correct? I think
Yeah.
Lazaro got it to work. Anybody else? No one else. Okay. Well, the others really need to try. Now that I have given you more details, you should be able to work this out. If you don't, please ask a question now, and before I move on to something else. Okay, so let's talk about and typing. This one, I think some of you had a timeout problem with the solution I gave last time. So let's quickly go over the problem. I see that there are new faces, so let's go over the problem again. The problem says the following. You're given a keyboard, but you could move the keys around. You don't have to have 1, 2, 3 up to 9. You could permute the keys any way you want. And there's an ant that wants to type out a message. And in order for the ant to go and type it out, it has to go over, step on the key, and then wait there for a second, and the number would get typed. And the question is, what is the minimum number of seconds that it requires, that's required for the ant to type out the message? So depending on the message, you could change the order, and some orders will make the ant walk around a lot, and others will make it walk around less. So the question is, how can you make it walk around the least possible amount of travel? So again, the naive solution is what we discussed last time. It simply says, try every possible permutation of the keys and compute the time that it takes for the ant to type out the message that's required, and simply report the permutation with the least time, right? Now, so in order for us to figure out whether this is possible, we have to do some counting on a simple piece of paper, right? And the time it takes depends on how many permutations there are of the numbers 1 through 9. And that we know is 9 factorial. And also the length of the message that the ant has to type. So let's assume that the message S has length S. Okay, I'm just using the same notation. So it's 9 factorial times S. We know that S is being told to us to be as large as 10 to the 5. So that's like 100,000. And we are told that, well, you can do some math on your calculator, and 9 factorial is somewhere in the range of 500,000, right? Or 3.
Math checks out.
Sorry?
It is somewhere around 500,000.
Can you type that in, because I can't quite hear you?
I think he said that, yeah, it is somewhere around 500,000.
Okay, all right, good, thank you. So, so if you multiply 9 factorial and s, it's a little more than 10 to the power 10, okay? Maybe somewhere in the range of 10 to the power 11. That's somewhere in the range of 100 billion. And last time I had guessed that this is going to work out. I think based on a couple of people who tried this out, I was told that it didn't work out. Is that correct?
Yeah.
Okay. So let's see what we can do to improve this. That's what we're going to talk about today. If you get time limit exceeded, here's what we need to do. All right, so here's an improved solution. We know the message that needs to be typed, right? So let's assume for a second that the permutation is fixed, meaning you have figured out what is the order of the keys, and that's what it's going to be. And remember, for each permutation, we have to figure out how much the ant has to walk. So let's see if we can speed up. Our goal is going to be to speed up how to figure out how much the ant walks for a given permutation. Okay. The way we did it in the previous naive solution was that we went through the message, started at the beginning, and went through each character and figured out how much it walked based on the permutation that you have. And that's easy to do, but it takes time that's proportional to the length of the string that you're checking. Now, how do I do this faster? Well, here's there's a nice little trick that you can use, but maybe I should open the floor to see if people have any suggestions. By the way, I'm going to assume that the permutation is given to you in an array. P sub 1 is the first key, P sub 2 is the second key, third key, and so on and so forth. So any thoughts on what I could do to improve this? Remember, the message is the same for every permutation. So if we could do some work at the start, look at the string that you want to evaluate, and somehow do a little homework before we start to look at every permutation, then maybe we could save time on each permutation, and that would speed things up. Does that make sense? So we want to pre-process the string in order to try and speed this up.
I don't know.
Any thoughts? Go ahead, Clement.
Could we remove duplicates or from the message?
Could we remove? Well, duplicates are important because that's the message the ant has to type. So we can't quite remove it. But duplicates are key because as the string gets longer and longer, a lot of the numbers are going to get repeated.
Mm-hmm. So could we do could we I guess store the previous results up to a certain point within a permutation so that when we check this said permutation, we already have those results? That's
actually a good idea. I had not thought of that. In order for that to go well, so you want to reuse some of the results so that other permutations could use this.
Yeah.
That's actually a great idea, but there's a lot of stuff to store.
Yeah.
You will need to build a permutation tree of all possible permutations and store quite a bit of information. Maybe not so much, but managing all that could be a bit of a problem. So instead, we're going to focus only on the string. Okay. And let's see what we can do with the string. Any ideas, brilliant ideas before I go on? All right. So here is the idea.
I think we're throwing them in the binary search tree or something like that. Like put them in a little tree and.
No binary search tree here. So let me try and channel you so that you can think this through better. Now, let's say that we have, I should actually show you an example first, isn't it? Pulling up an example is a bit of a pain. Do you see the browser? Do you see the PDF file?
Yeah.
I'm still seeing the slide.
You do. Okay, good. But it's not showing the right problem.
Wait, by PDF, do you mean the slides, or is there something else?
I'm talking about the problem set. Do you see the problem set?
Oh, no.
Just the slides.
Okay, all right. Let me see if I can fix that. Okay. All right. Do you see the problem set now?
Yeah.
Yeah.
Okay.
Oh, yes.
So and typing is the problem we're looking at, right? Now, let's look at the message here. So here's the message the ant is supposed to type out. Alec, can you mute yourself? Thank you. So here is the message, 784325579. Now, this one is not a very long message. Imagine that your message is how long it can be, 10 to the 5, right? So imagine that you have thousands of numbers that the ant has to type out. Now, the first one goes from 7 to 8. Then it goes from 8 to 4. Then it goes from 4 to 3, and so on and so forth. Now, if you look at, if the message is long enough, what would happen is that 7 to 8 is going to appear somewhere in the string, most likely. 8 to 4 most likely will show up somewhere else. 4 to 3 will also show up somewhere else. Now, every time 4 to 3 appears, it's going to cost the ant the same amount of time. So I don't have to go and figure that out one more time, how much it would cost the ant to go from 4 to 3, because I knew that even before. So what could I possibly do that might help me?
If we know that pair, how many,
Yes.
the frequency of that pair, then we know
Yes.
when we first see it, we can
Excellent.
multiply that length by that frequency.
That's right. So all I have to do is to process the string and figure out how many times I go from any digit to any other digit. And I do this for every possible pair of digits. So for every pair of digits m and n, I will figure out how many times m is followed by n in the string. And let's say I do the statistics right at the start. Now, how much time is the ant going to require to type out the message? Well, it's quite easy, because if the total distance that the ant would travel would be, you want to give me a formula now based on what you see here?
The total distance would be the length of the message time, like the.
No, you have to use the thing that you just computed up there, T m comma n.
Tm, comma n.
So I'm using a notation Tm comma n to tell you how many times m is followed by n. So I have t of 1 comma 2, I have t of 1 comma 3, I have t of 1 comma 4, etc., etc.
Yeah, it would be sum of all of them.
Exactly. Well, not quite some. Better answer, anyone? So you remember TMN is a frequency, right? It tells you how many times this pair occurred next to each other. So I don't have to go and figure it out every time. If it appears 47 times, there's no need for me to add the same number 47 times. I can just multiply that number by 47, right?
Right.
But what am I multiplying by 47?
The distance between the pair.
Exactly. So you just told me the answer. So I'm going to compute the number of times m is followed by n and multiply it by the distance between the position of keys m and n, which is the absolute value of pm minus pn. And remember, P1, P2, P3 is, so I'm sorry, I actually messed this up. It's not PM minus PN. Yeah, I made a mistake here. So the key order is, it's actually the position where
the key, where a certain number is within the keyword.
Yeah. So P of 1 is the place where 1 occurs. P of 2 is the place where 2 occurs, and so on. So I'll fix that sentence, okay? So that's not key order, but it's actually the location of those keys, okay? So PM minus PN will tell you how much the ant has to travel in going from m to n, and we know it occurs t of mn times. So you just multiply those two and total it up for all the possible pairs of keys. Now, we understand this clearly, I hope. If you don't, please ask me. Now the question is, how much work does this require? So remember, we're summing this over all possible values of m and n. Now, how many pairs of values m and n are there? What are possible values for m? And what are possible values for n?
Any of the possible keys.
1 through 9, right?
Yeah, 1 through 9, yeah.
So possible pairs m comma n, how many are there? 9 times 9.
Yeah.
So there's only 81 pairs. I just keep track of all these 81 pairs, and I keep track of the frequency of how many times m is followed by n. All right, so essentially it'll be a big table, 2-dimensional table, right?
Right.
It'll tell me how many times 3 is followed by 7, or 2 is followed by 9, and so on and so forth.
Oh, okay, yeah, I understand. That's clear.
Yeah?
It's clear now, yeah.
So you first go and create the table from the string, and then you don't have to now go through the entire string. You can do something very, very fast. And what are you doing that's going to be very, very fast? You just figure out this formula here. Whatever is in the table, Tm comma n, and multiply it by the distance between those keys. And do this for every entry in your table. Add them up, and you're done. Is that clear?
Yeah, that's clear.
Okay, so our next job is to figure out how long this is going to take us, right? Is this as expensive as our previous solution?
No, we're saving a lot of time.
We're saving a lot of time, right? So
Yeah.
let's figure out how much we are saving. Let's actually do the math. So we are going to first look through the string, and we're going to focus on pairs at a time, consecutive pairs. So the amount of work we're going to do is proportional to S. And for each pair, we'll go and increment the count of some entry in a table. Right?
Right.
And so that's going to be S. That's the length of the string. And then we're going to add to it. Now we're going to do the work for every permutation. That's 9 factorial. For each one of these, the amount of work we have to do is 9 squared, because that's the number of pairs we have to deal with.
Mm-hmm.
So we just apply this formula here that you see, T of m comma n times absolute value of Pm minus Pn. We do this for every m and n, and then we'll be done. So this is the amount of work we need. And 9 factorial is about 500,000. Multiply that by 81, or let's round that up to 100. So it's going to be 50 million, okay? And add to that another 10 to the 5, another 100,000. So it's still somewhere in the range of 50 million. That's nothing. Your program will run like a breeze. Is that clear?
Yeah, that's good. Sounds good.
So we know this is somewhere in the range of, well, I've said here 10 to the 5, but actually that's incorrect, because 9 factorial is 500,000, 9 squared is 100 roughly. So it'll be 10 to the 7, or in the worst case, 10 to the 8, and still that's very, very small. You can easily get that to run in 1 second. Now here's some code that will show you how this is done. So our first job is to go through the string. And so we are going to look through the entire string, going from second position all the way up to S. And for each one, we are going to increment the frequency of going from the previous entry to the next entry. Remember, previous is whatever was in the previous location, and the next is an S sub k is whatever you're looking at. So just these 4 lines of code will take care of building your table called T.
Mm-hmm.
If this is not clear, please stop me and ask. And so once the table is done, for every permutation, you just have to go and do some computation. I didn't write that down, but hopefully it's simple enough. Any questions?
There was one in chat.
Yeah, I'm looking. Yeah. Can you use supremum of the distance between number of pairs? Well, that's essentially what we are doing, Aussie. It's just that in order to figure that out, we are speeding up that calculation. So what I haven't written in the code was that you still have to go through every possible permutation, and for each permutation, you have to compute the total amount that the ant has to walk. It's just that in order to figure out how much the ant walks, I don't have to go through the whole string. Instead, I will just look up the table and do some few calculations, and that'll be done. Everyone okay with that?
Yes.
Okay. All right. So are we ready to move to the next problem?
Already.
All right. Lazaro had asked me about problem I, and it's possible that not all of you have read this problem, so I'm going to tell you what the problem is. Okay?
No.
Did you try this, Clement?
Oh, yeah, that's actually funny. I saw this question in the competition, and I just was like, oh, longest common subsequence, and so I just thought it was like the like default question where it's only dealing with 2 words. I didn't read the entire problem statement, and I just blazed through.
Okay.
I was like, oh, I
Yeah.
got a solution, and yeah, but I didn't.
Obviously, it didn't like your solution.
Yeah.
All right. Anybody else read the problem? Samara, did you read it?
Okay. Unfortunately, no.
Okay. Okay. All right. So let me explain what the problem is. It says that you're given n of n strings, and each string is a permutation of k uppercase letters. Okay. And you're told to find the longest common subsequence. Now, the definition of a subsequence is that S is a subsequence of T. If you can find S in T, it doesn't have to be next to each other. It could be spread out throughout the string, but it has to be in the right order. Is that clear? So for instance, if your word is subsequence, then B, Q, E is a subsequence. They're not next to each other, but they're in the right order. B is followed later by Q, Q is followed later by E. All right? So that's a subsequence. Now the question is, how do I find the longest common subsequence of all the n strings? Now doing this for a pair is easy using something called dynamic programming, which we haven't talked about, but at some point we'll discuss dynamic programming sometime pretty soon, and you'll know everything about longest common subsequence by then. But this problem is a little different. In fact, it turns out to be way easier than the other longest common subsequence problem. So let me tell you more. So again, you're told that n and k is given. N is the number of different sequences you have. Remember, each one is a permutation. And k is how many characters you have on each string. So every string has the same number of characters. Every string has k unique characters. None of these are repeated. And you're given n of them. So you might be given 100,000 of these strings, but each one has at most has exactly k characters, and they're all distinct. Fine. And your output, of course, simply is you're asked what is the length of the longest common subsequence. So let's do a simple example, make sure that we all understand this. So on the left, you see 3 sequences. They are the letters A through H. And on the right side, I did make a mistake. On the right side, you see the subsequences. And the subsequence is HCE. I forgot to make the E red on the first one, but I think you get the point, right? So I want each of you to understand how HCE is a subsequence of each of those 3. Is that clear to everyone?
Yes.
Yeah, they don't necessarily have to be contiguous.
They don't necessarily have to be next to each other, but they are in the right order. The order is very, very important. Fine?
Fine.
Okay. Now, our job is we're given the sequences on the left, and our job is to find the longest such subsequence. Okay. By the way, AE is also a subsequence. There are other subsequences here. Okay. The question is, which is the longest one? Or what's the length of the longest one? That's all we need. Now, so really for in this example, we're asking, could it be 4? What do you think?
Yes.
Okay, do you see 4? Which one?
GFCE.
GFCE, GFCE. GF. I screwed up because I mistyped. This one is not GFCE. As you can see, I really screwed up here. Let me fix this. Lazaro is sort of right, but it's because I screwed up. Let me fix that. Give me a second. All right. Let me first make. All right, this one is really H, C, F, G, B, D, A, E, and I need to make E red. Okay, now we have it right. Okay. Oh, it went off somewhere else. All right. So let me ask the question again. Do you think there is a longest common subsequence of length 4?
Not that I can see right now.
Not like, yeah.
I think it's H. Oh, no, never mind. No.
Yeah. So it looks deceptive, you know, and if here you're only given 3 sequences, so it's easy for us to eyeball this. If I gave you 3,000, we're going to be in trouble, right? So we need to come up with an algorithm for this. And so let's first think about a simple solution. Give me just a second. Yeah. So first of all, we know that in the input there are n sequences, and each sequence is a permutation of the exact same k characters. Okay, and they are uppercase characters, just to be clear. So what's a naive solution? Let's not worry about time. Let's not worry about whether it's going to finish quickly or not. Let's just think about a solution that works. Can you think of a solution that works?
Finding a subsequence in the first string, any subsequence, and then see if any of those.
So you would like to, so you want to try every possible subsequence of the first guy and check them in the others.
Yeah. And then save the largest one. And
you keep track of the largest one. Sure. So that's definitely a solution that would work. So essentially we want to try all possibilities, or at least lots of possibilities, exhaustively. So we could try, actually Lazaro's solution is slightly better than this. My solution, naive solution, is even more naive. It says, let's try every possible permutation of every subset of k characters. So it's not just k characters, we are also trying every subset of k characters, okay? So we don't have to include all of them. We also want to try some smaller ones because our longest common subsequence may not use all k of them. Now, the question is, how many of these do we have, right? And in order to figure that out, we need to do some counting. How do I count? how many such cases do I have to try? So if you have k items, how many permutations of k items?
K factorial.
Good, yeah. So that's k factorial. So, and then how many different subsets of k characters are you likely to have? How do you count number of subsets? That's called the power set, right? You remember this from your discrete math?
Yes, I just don't remember the exact.
So it's very simple. Think of binary numbers.
Mhm.
If you have a set of k items, and if you want to know how many different subsets you have, just think of binary numbers of length k. If you have a 0, drop it. If you have a 1, keep it. So all the ones that are there will tell you which items you want to create a subset out of. Okay. Now, that means for every binary number, you'll get a different subset. So how many different binary numbers do you have of length k? Yeah.
Professor?
Yes.
The way that you're sharing your screen, it gives away the answer sometimes.
Oh, it does? Okay.
Yeah. So we
see.
can see it's 2 to the k times k factorial.
Okay, let me fix that. I think there's the swap something screen. Yeah. Now?
Yeah, now we're looking. Yeah,
Okay.
perfect.
Thank you for warning me and not embarrassing myself. Yeah. Okay, cool. Right. So, so you already know the answer then. It's 2 to the k times k factorial. And that's because, first of all, you're looking at all possible subsets of k characters. That's 2 to the k. I just explained that to you, right?
Mm-hmm.
And for each one of these, you're doing permutations. And so k factorial is a upper bound, so it's okay. So it's something very, very large. And since k is 26, this is an absurdly large number. There's no way we're going to write a program that will take care of something like this. Okay, because 2 to the 26 itself is something like 65 billion. Sorry, is it? 2 to the 20 is roughly a million. 2 to the 26 is 65 million, roughly. So let's say 100 million there, 10 to the 8. And k factorial, 26 factorial is enormous. I will need a calculator to figure this out. So there's no way we're going to be able to try every possible permutation. So we've got to do something smarter. All right. I hope you didn't see the next slide.
No, this is as far as we saw.
Okay. So we've got to come up with some new ideas. That's what this means. Now, let's figure out some good observations that would be useful for us. Okay. Here is a simple observation. Let's say that let's say somebody gave you the answer and said, here is a subsequence that's the longest common subsequence for all of them. Okay, you can easily verify this, no problem. All you have to do is to make sure that the characters appear and in that correct order in each one of them, right? But if it's a longest common subsequence, let's say we just take the first 2 characters. Let's say we only take x1 and x2. What we know is that if it is the longest common subsequence, then x1 must be before x2 in all the n sequences. Agreed? Okay, so we all agree on this. That means if you have a longest common subsequence x1, x2, x3 up to xm, then all those M characters must appear in that same order in every string. This is going to help us. In fact, what we are saying is it's enough just to focus on two of them. We know that if x1 is always preceding x2, then I could make a common subsequence that has x1 followed by x2 sometime later. Is that clear? In fact, if x1 is not followed by x2 in all of them, even if one of them has x2 before x1, then it's never going to work out. Right? So what do I do? This is a nice observation. What do I do with this?
I think I have an idea.
Go for it.
We can try to set the first string as our longest common subsequence, and then check with the next one and see which letters are we can remove. I don't know.
Maybe.
Yeah, well, you're not using the first observation that I have here on the slide.
Okay.
Oh, I haven't shown you this.
Yeah. Okay.
Now it's showing up. Sorry. So if you have the longest common subsequence, for every pair of characters there, x1. So let's say x1 is followed by x2 in your common subsequence. Well, what we know is that x1 must come before x2 in each one of them. There cannot be any exceptions. How do I use this?
I was okay. I was thinking like maybe we could do something where you like try a certain sequence from like the first string and see like if the ordering happens.
both of you, Clement, Samara, you're stuck in the old problem of longest common subsequence.
Okay.
The moment you get your head out of that, you're going to figure this out very easily.
Okay.
So focus on this observation. This is very, very key. Okay. What this says is the only things that will help you to form the sequence is if for every pair of characters in there, the order is consistent across all n sequence, all n strings.
So would it just be checking if for like an x1 that happens before x2 in all the subsequences?
Yeah. So how do I do this? So here's the idea, which essentially is what you just said. Let me do this for every possible pair of characters. How many pairs are there?
There's 2 to the k. No?
How many characters, how many pairs are there? Pairs. How many pairs are there?
There's
okay, in order to figure out how many pairs there are, how many different ways can you pick the first guy? How many characters are there?
There's k characters.
K characters. So the first one, you have k choices. The second one, how many choices?
K minus 1.
Done. So how many choices? K times K minus 1. How much is that?
Gosh, I was overthinking.
How much is K times K minus 1? Roughly K squared.
K squared, yeah.
Not 2 to the K. It's not 2 to the K. Okay.
Yeah.
K squared is way smaller. 26 squared is much smaller than 2 to the 26.
Yeah.
Okay. So 26 squared is somewhere like 700 or so. Whereas 2 to the 26 is what I told you, something like 60 million.
Huge. Yeah.
Huge. Okay. So for each such pair, what are we going to figure out? We're going to figure out whether it's allowed for xi and xj to appear in the longest common subsequence. And if so, in what order? Could we figure this out? We're not trying to figure out the common subsequence yet. All we are saying is, are we allowed to have xi and xj in there? So think of your previous example with the h blah, 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 right?
Right.
I want to pick 2 characters. Let's say I pick C and F. And I want to know, can you have C and F in your longest common subsequence? And if so, in what order should it appear? That's all I want to know. Do you think we could figure that out in that example? Let's go back to the example.
That would just be checking if C.
So let's take C and F. Do you think C and F would be in your would be part of a longest common subsequence?
No, because F.
Why not?
Oh,
because in the first case, F came before C, so it's never going to happen, right?
Right.
Great. So let's pick another example. Let's say B and D.
No.
Again, no, because the second string has D before B. Done. Those 2 are never going to show up.
Oh, yeah.
Okay? So start kicking things out.
Oh.
And we know there are only, 81 pairs, right? Sorry, not 81, 26 times 25. So about 600 pairs. So now what do I do? Any thoughts? So here's what we're going to do. We're going to talk a little bit about graphs. Let's create a graph. Here's my graph. I am going to create. Remember those strings that you saw, those 3 sequences you saw. They were 8 characters, A through H. I put them down here. Fine. Now I'm going to try each pair and figure out whether it's allowed or not. I should have copied those sequences here, but you just have to trust me that H to F is allowed. That in each of those, H comes before F. So I make an arrow from H to F.
So would this be like a undirected graph?
Cool it.
Sorry.
Everything is conceptual. Everything is conceptual here.
Okay.
Oh, thank you. Somebody made that. Appreciate that, Lazaro. Oh, Samara? Yeah. So those are your sequences. You can see here that in each case, I start to look at pairs. Okay. Let's say I look at H and F. Sorry, let's say I first look at H and G. H and G appear in the right order in the first sequence, but in the second sequence it doesn't. So that edge is never going to be there. H and the next guy, H and B, same problem. Then H and D, same problem. H and F is the first thing that I allow because it's consistent in all of them. So I make an edge that goes directed from H to F. Why? because H has to show up before F, right? Are we cool? Okay, next. I will try H to C. Is that okay? H to C is okay, so I'm going to put that H in. Oh, sorry. Are you fine?
Yes.
I continue this process for every pair of vertices. And when I'm done, it's going to look like this. I think I'm done here. Now what do I do?
Well, I see that E is the one that everybody's pointing at. I would think that's the last one. I don't know.
Well,
Maybe.
what's a possible solution here?
You take the longest route and count the number of nodes.
That's right. You just find a path. Because all these edges are okay. All these orders are okay. So what's the longest path in this graph? Now, here's a path that goes from H to C to E. That's of length 3. There's another one, H to F to E. I'm sure there are paths of length 2 somewhere, but 3 seems to be the best. I cannot find a path of length 4. So 3 is the answer. So essentially, if there is a longest common subsequence, that must show up as a path in here. Now, the nice thing is that this graph doesn't have cycles. So these are a lot easier to deal with. So now it brings us to the next problem. How the heck are we going to find the longest path in this graph? Is everyone fine with what we've talked about so far? Aussie, Alec, David? All good?
Yeah, all good. Oh, on this path in the graph?
Any ideas?
Since we know it's acyclic, can we just go through each and every single letter?
Going through, so I don't know what it means to go through every single letter because I don't know where to start.
Okay, can we set up something like where we map like a character and then the letters that come after it, like
Good, yeah.
and then
that's good.
And then like we do a depth first search of that.
Very good, yeah. So it turns out that something close to that works out. In fact, this is, we will talk about graph algorithms sometime soon. So we haven't quite seen this yet, but this is called topological sort. So if you've seen this somewhere, well and good, but it's pretty straightforward. Okay. Now, what the heck is topological sort? You already know this?
Kinda. It's like
kinda.
Yeah, okay. You're given like a directed acyclic graph.
So all right, go for it.
And basically with it with topological sorting, there can be like no cycles within the graph.
Yeah, that's what this is, directed acyclic graph.
Yeah, and it's used to like keep the ordering of certain
Lazaro, remember something?
I remember the name, but I also know you have to choose a node, and I think you have to remove it and then count
Yeah.
the number of edges.
Yeah. So what we do is we go to the vertex that has nothing coming in.
Okay.
Which one would that be here?
H, G,
H.
B, D.
So there are a bunch of them. We're going to number all of them as 1. Good. Because there's nothing coming in, you could go and start there. So your path can start there, and you are likely to find the longest one from somewhere there. That's all it's saying. Now, what do I do with the rest? So I remove all the guys that are labeled 1, and whatever is remaining, I label, whatever you can reach from 1, I'm going to label them as 2.
Mm-hmm.
Which ones would that be?
E, C, F.
Oh, you're saying E also?
Well, technically, because H can
So
go.
I have to be, yeah. So you can only label something if everything from which it has an edge has already been labeled.
Oh, okay.
Okay, that's what topological sort will require. So so I can only label C and F as 2. I cannot label E because E also has edges from C and F which have not yet been labeled,
Mm-hmm.
right? So before coming here, I cannot label E because it has other edges besides the ones that are labeled 1.
Okay.
Is that clear? Whereas if you look at C and F, it only has edges from vertices labeled 1. E doesn't satisfy that. So I can label C and F as 2. And now I'm left with only 1 vertex and all its predecessors are labeled. So I can label it the next thing, which would be 3.
Yeah.
So that's your longest path. It tells you immediately. And this, by the way, is breadth first search, except that you're not doing breadth first search from a single vertex. You're doing it from all the vertices that have no edges coming in.
Mm-hmm.
Clear?
Clear.
But anyway, in the literature, it's called topological sort. You just take the code and dump it in here and it should work. And at some point, we'll discuss this in class and you can learn the details. So in order for this to work, you have to find vertices that have no edges coming in. How do I do this? So for that, you have to work with the graph. You have to work with the graph representation. You have to figure out which vertices do not have edges coming in. Okay, and if you keep count of, so if you first go and process all the edges, you will know which ones have edges going out and which ones have edges coming in, and you have to keep track of them. So a topological sort is it's easy, but it's not trivial. So you may have to look at the code in order to convince yourself that the thing works. But the picture I showed you should be pretty clear, and I hope that you understood it. Okay, so we went from sequences and permutations to graphs and longest paths, all right? And this is part of problem solving. This is where some of your experience and your tricks come into play. Somehow you have to model the problem differently and start to think about it differently. And suddenly you'll see something else that will make it work. And many, many problems will have this flavor where it's a lot easier to think about it in a very different model. Okay. This problem, I think, is totally doable for you guys. You could have done this, but mapping it is not so easy. That takes some experience. And this is part of what you learn in this Thursday sessions. Okay, how to take problems and model them in different ways so that suddenly they become clear.
Mhm.
Okay. So I think this is a really nice problem. Not too hard, not too easy, but it requires a little jump. And by the way, there are other ways to solve this. Using graphs and longest path is not the only way to do it. I'm sure you can come up with other ways to do it as well. But I think this is conceptually quite simple and makes for easy solutions. And one of the most important pieces of solving this problem was to figure out this observation that oops, sorry. Yeah, this observation here that says that if you have a solution, then you can take every edge on that path or every pair of that sequence, and that ordering must be true in all the permutations. If it misses in any one of them, you can throw it out. In fact, anything that's not consistent across all the sequences, you can eliminate it right away. They don't even have to show up in your picture, right? And that helps because then you're able to eliminate a lot. Now, I have a question for you. You all understand how I went from this observation to this graph here, right? You remember this. And you understood how I created the graph. Now, I need you to tell me why this is acyclic. We all understand why it should be the longest path, but why is this thing acyclic? Why can't you have cycles?
Because we checked that AI wasn't, no, I don't know how to explain that. One word wasn't after the one. Yeah.
Prove by contradiction.
So we proved that, well, through the process, it's not possible to have.
What does each edge tell us? What is the meaning of any edge?
That, for example, F is always next to
before, not next to, before.
Yeah, before the E, for example.
Right.
Not
so
after.
If there is an edge from F to E, then F is always prior to E in every sequence, right? So if there is a cycle, how can the cycle happen? It must go from something to something, then something to something, then something to something, and then it must come back. Well, that means this guy is before that guy is before that guy is before that guy is before that guy, and then it comes back. Is that even possible? Nope. That's a contradiction. That's why it's acyclic. And because it's acyclic, you can use topological sort.
Oh, that actually, it makes a lot more sense why they told you that it only occurred exactly once.
What occurred exactly once?
Oh, each uppercase letter only occurs exactly
once. If it were not a permutation, this thing wouldn't have worked out so well.
Yeah. Oh. Yeah, that makes sense.
So there are lots of pieces here that need to fall into place, but it's definitely not, conceptually, it's not hard, right? It's not like it's using some fancy things. All right. I have only about 5 minutes. What's the next problem you want to talk about? Because I haven't prepared it. What I suggest for you is to go back this Saturday. I want to see you guys submit correct solutions for all these problems: A, F, I, and P. Is that?
I tried P, by the way. Sorry.
What about P?
Yes,
you tried P? Yeah.
Yes, but I couldn't do it even with our algorithm that we created last time.
Yeah.
Let me see, because first I did it in Python and it told me time limit exceeded, and I thought maybe it's because of the language, which it didn't make sense. But I tried with C, and then now it tells me memory limit exceeded. So I don't know.
Yeah. So here's the problem. We can go through it quickly.
Okay.
So you're given 10 to the 9 people, right? And so you're given n people, and they send m messages. Each message is sent by one person to everyone else, and everyone reads their messages only when they send a message. Until then, they don't read their messages, like most of us. So all we have to do is to count the total number of unread messages at every given time. And we saw how we were going to do this, right? We talked about this last time, and the code was pretty simple. But of course, implementation, and there are always little things to worry about. And I think Lazaro also told me that you had to use a hash map in order to get this to work.
For Python, at least, with an array would have given you time limit exceeded.
I see. So, so perhaps Samara, that's have you tried the hash map in there or not?
No, okay. I will try that.
Yeah. So I think Lazaro, according to as far as Lazaro's experience goes, changing from array to hash map made the difference. And that may be because this array is pretty large. This 10 to the 9 is pretty large. It's possible that hash map somehow it sets aside a much larger scratch space or something like that. So it has to do with some quirk of Python. It's not really an algorithmic trick at this point. I think we figured this out pretty well. It's just a matter of kind of pushing it through at this point.
Yeah. Okay. Thank you.
Okay. And how big was your code, Lazaro? Pretty short?
Oh yeah, really short.
Yeah. Yeah, very good.
Professor,
so if you still have trouble, Samara, let us know. But I think it's really not a difficult problem. I'm sure you can figure this out at this point.
Thank you.
Professor, you think for next week we can go over triangular collection N and bad packing B?
Okay, let me see what they are.
I know Clement really wants those questions answered.
Clement is panicking already.
Oh my gosh! I don't know. Well, the triangular number just.
Well,
oh yeah, that one
slowly.
Sucked.
Which one is that? N?
Yeah.
Oh yeah. Yeah, sure. We can talk about this next time, but would you like a hint here?
Yes.
Yeah. Yes.
How many of you tried this? So at least 3 of you tried this? Okay, good.
Yeah.
So the hint is right. So if one side is of length 3, other side is of length 4, and the third side is of length 200, is this ever going to work out? Wait, what are you given here? If it has Yeah. So, so let's say I have one. I tell you, I've just created a triangle where one side is of length 3, the other side is of length 4, and the third side is of length 200. Do you think this is even possible? And if not, why not?
With the 3 and 4, we could make a triangle, but we have like a tail. Would that count?
Well, it has to be precisely 3 and 4. You can't do anything else. Can I make a triangle where 3 sides are of length 3, 4, and 200?
No.
Why not?
Well, if one side is 200, then some of the other sides has to be kind of close to that if it's the longest
Very
side.
good. In fact, there is something called the triangle inequality that says that the sum of the other 2 sides must be at least as large as the third side. Okay, because the one side is of length 200, that means the distance between those points is 200. You now are trying to make 2 other sides, and that total length is going to be at least as large. But 3 plus 4 is not 200 or more. That's the rule that you have to just repeatedly apply here.
Okay.
That's your hint. Of course, that doesn't necessarily solve the problem, but hey, that's your start point. Okay?
Okay.
Thank you, David. That was good.
No problem.
And what was the other one?
Bad packing, B.
Yeah, this might be dynamic programming, but we can get started on this. Yeah, I think sooner or later you have to get to both dynamic programming and graph algorithms. So we'll slowly try and learn both the theory and and solve some problems. Okay. Yeah, if there are other problems you guys want to go and take a crack at it, please do. And please report me if
I'll
you
start
solve.
today and tomorrow.
Okay, please report to me if you solve anything other than what we've discussed. I would love to hear something like that. Okay. All right, guys, and do show up on Saturday. So are you okay with leaving it the same set of problems, or do you want new ones already? I think you should go and get them to work, at least the ones we've discussed in class. Is that fine with you? Okay.
That's fine.
All right.